Going to look at another distribution. This time it's the binomial distribution. So it follows on from what we were talking about yesterday with binomial probability. Because basically, well, you can see the definition there, binomial distribution consists of n repeated Bernoulli trials, which essentially is what binomial probability was. X will represent the random variable denoting the number of successes in the Bernoulli trials, and there is the formula, which is exactly the same as the binomial probability formula from yesterday. The only difference is I've put 1 minus p instead of q. Okay, so p's probability of success, x is the number of successes, and n is the number of trials. All right, well, let's go and calculate out what the expected value and the variance would be. Now, before I start on this, do not panic. They won't ask you to prove this. I'm just showing you where it comes from, and I need to do a little bit of manipulation for it to work. So expected value would be the sum of px, but at this stage, what is the sum? Well, we know that if it's naught, then it's nc0, p to the naught, q to the n. If it's 1, then it's nc1, p to the 1, q to the n minus 1, and so on and so on and so on. So we want to sum all of these things together, because it's going to be x times px. So we'll end up with the sum of k, nck, p to the power of k, and what have you. All right. Well, the first thing I'm going to do is I'm going to pull out that first term of 0, because k is 0, so that particular term will end up being 0 anyway. So my new sum is just going from k equals 1 to n of this expression. Well, what I've now done is I've rewritten it. So essentially, remember, nck would be n factorial on k factorial, n minus k factorial. So I've factorised the n out. So now on the top of the fraction is n minus 1 factorial. But I've put the k back in, which turns it into n minus 1 ck minus 1. Trust me, I mean, I could do the algebra on there, but as I say, it's not something you need to prove. It does work out to be that. But I'm not going to leave it there. Now I'm going to factorise out some constants. Well, n is a constant, so I'm going to factorise it out. P and Q are obviously constants as well. I'm not going to pull everything out. I'm just pulling one of the p's out. So that reduces the power of p down to k minus 1. Now the reason for doing that is because now what I've got, instead of going from k equals 1 to n, I'm going to say I'm going from k equals 0 to n minus 1, which means instead of n minus 1 ck minus 1, I have n minus 1 ck, because I'm starting at 0 instead of 1. It changes that, because now essentially that's the sum of a binomial product, which would just be p plus q to the power of n minus 1. Why do that? Because we know p plus q must add to give 1. And I come up with a definite answer. But that's all we need to know, is that very last line there. The expected value would be n times p. Now let's work out the variance. This one's even better. So it'd be the expected value of x squared minus the average squared. Well, I'm going to rewrite the expected value of x squared as x times x minus 1 plus x. That is x squared if you work it out. And then from there I'm going to break it up, because we know the expected value of x is np. So I've worked that bit out. So now I just need to work out what the expected value of x times x minus 1 is. All right. Well, that would end up being the sum k minus 1, nck, p to the power of k, q to the power of n minus k. And now I'm going to start playing around with this one. I'm going to pull out the terms that I know are going to be 0. But in this case, it'll be when k is 0 and k is 1 that will end up being 0. My sum now is 2 to n. All right, we're doing a similar thing to what I did before. I'm going to factorise out the n, but also the n minus 1 this time. But I'm going to put back in the k minus 1, which means I now have n minus 2 ck minus 2. That one, I'm going to pull out the constants n minus 1, but also a p squared, leaving me with this expression. Now, that expression becomes p plus q to the power of n minus 2. But p plus q we know is equal to 1, and we end up with n times n minus 1 times p squared. All right, but remember, we've also got to add in np and take away n squared p squared. So eventually, we end up with just this, NPQ. Again, that's all you need to know, NPQ. Don't worry about how I got it there. So let's summarize that. If X is binomially distributed, so BIN for binomial, the two pieces of information we need to know is N, right, the number of times we're doing it, P, the probability of success. We know the expected value will be NP, the variance would be NP, well, instead of saying NPQ, I'm saying NP times 1 minus P. Here's the interesting thing with a binomial distribution. It's a lovely distribution. If the probability of success is less than a half, you will end up with a distribution that is positive skewed. If it's equal to a half, then you'll get a lovely symmetric distribution. And if it's greater than a half, you'll get one that's negative skewed. We're going to state whether a binomial distribution could be used in each of these problems. And if it could be, we'll work out then what the random variable is describing and all the different information we'd like to know, its parameters. So a fair cubical dice, 6-sided, is rolled 10 times. Find the probability of getting 3 4s, 4 5s, and 3 6s. So the question is that a binomial distribution? And the answer is no. Because there's 3 different outcomes we're interested in. 3 4s, 4 5s, and 3 6s. So it's not binomial. Remember, binomial only had success, failure, 1 outcome. So if we wanted just the probability of 3 4s, and we're only interested in one thing, that would be okay. Or alternatively, if it's just the 4 5s or just the 3 6s, that's okay. But in this case, there were 3 different outcomes we were interested in. We want a single outcome. No good. All right, a coin. We're going to just keep tossing it until a head happens. Find the probability that 8 tosses are necessary. Would that be a binomial? And in this case, no, because the number of tosses is unknown. We're going to keep going until we get a head. We don't know how many tosses that's going to be. So when we're talking about a binomial distribution, we need to know the number of events. Remember in that distribution, I said the 2 things we need to know. N, the number of times we do it, and P, the probability of success. So we don't know that. That's not a binomial distribution. So the random variable here, what we're interested in is the number of tosses. And so again, we don't know how many that's going to be. A jar contains 49 balls. They're numbered 1 to 49. 6 of the balls are selected at random. Find the probability that 4 of the 6 have an even score. No, in other words, an even number of them. Well, in this case, it depends. Is it with replacement or without replacement? You see, if it's without replacement, then it's not binomial. Remember we saw that yesterday with binomial probability. Probability has to be the same every single time we do it. So that's no good. But if it is with replacement, yeah, this would be binomial distribution. X, our random variable, will be the number of balls with an even score. There's just one thing we're interested in. We know how many times we're doing it, so everything's fine. So it would be binomially distributed. We're doing it 6 times, and the probability of success, the probability of getting an even score, or 24 out of the 49 numbers would be even. So the probability is 24 over 49. So if I actually solve the problem then, it's our binomial probability question. Probability that x equals 4, 6c4, power of success to the power of 4, power of failure to the power of 2, power of failure, probability of failure to the power of 2, and there we go, to 4 decimal places, 0.2247. So we've got 3 trials of a binomial experiment. The probability of x successes. So we can have 0 successes, 1 or 2 or 3, and there's the probabilities that we've been given. Find the probability of success at 1 trial. So we know it's binomially distributed. We know we're doing it 3 times, but it's P that we're trying to find. What's the probability of success? I'm going to pick 3 to make life easy for myself. Because if I say probability of x equals 3, we know it's 0.027. That's what they told me. Well, using our binomial probability formula, that really is, when you look at it, simply saying p cubed is 0.027. So we can work out p. Cube root of that is 0.3. What would the variance of that distribution be? Well, okay, we said it was NPQ, but Q is 1 minus P. So NP, 1 minus P, just a matter of substituting in 0.63 is our variance. Here's 3 graphs. Which one is which? Who remembers which way around it goes? One of those is symmetric. I think that's the easy one to pick. One of those is positively skewed, and one of those is negatively skewed. Well, no prizes for guessing the first one is the symmetric one. But which way round does it go? Which one's positive? Which one's negative? I always think it's the wrong way round. That's the one that's negatively skewed because the numbers are going to the positive side. That's the one that's positively skewed because the numbers are going to the negative side. That's why I always think it's the wrong way around, but that's why. So whichever way it's pushed, it's sort of the opposite, if you get what I mean. But then, looking at those 3 distributions, which one is more likely to have an individual trial with a probability greater than pi on 5? Pi on 5, what's that? 3.14 divided by 5. 0.6, I was way off. But it's more than half anyway. Okay. Well, so the answer is B then, because that is more than a half. And so we want the one where the data's skewed towards things that are more than a half. So it's the negatively skewed one that would be the answer there. X is a random variable. It's defined. We're doing it 150 times. Probability of success is 2/5. Find the mean and the standard deviation of this distribution. Well, we said the mean was just simply n times p. Kind of makes sense when you think about it, n times p. Probability of success times the number of times you're doing it. So 60 it ends up being. Variance, I have to work out before I can work out standard deviation. That works out to be 36, so the deviation is 6. Well, how many more trials would I need to increase that mean to 100? So it's 60 at the moment, I want it to be 100. Probability of success hasn't changed, it's still 2/5. So I'm going to need n to be 250. So, but the question says how many more? So I need another 100 trials. But what effect does that have on the standard deviation in the distribution? Well, standard deviation is now 7.75. So it was 6, it's now 7.75. What does that tell us about the distribution? Well, what does deviation measure? Spread. So therefore, my data must be spread out more from the mean. It's got a bigger deviation. Here's our experiment. 2 dice are rolled 10 times. The number of times the sum equals 7 is noted. Find the mean and standard deviation of the distribution. Okay, so X is going to be the number of times the sum is 7. That's what we're interested in looking at. It's binomially distributed. 10 times we're doing it. Probability of getting a 7, or a total of 7, is 1 in 6. It's the most common outcome when you're rolling 2 dice. So the average is 1.67. The deviation turns out to be 1.18. We're going to simulate that. We're actually going to go and do it 1,000 times. So we're not rolling the dice 1,000 times. We're actually rolling the dice 10 times 1,000 times. So that's a lot of rolling the dice, and trust me, I didn't do it. I got a spreadsheet to do it for me. But there's the data I got from the spreadsheet. Now, experimental data is always different to theoretical data unless you get incredibly lucky. And so this is what I ended up with. You can see that I never ended up with a frequency of 8, 9 or 10, for instance. So the mean and standard deviation of that simulation. Okay, well, the average is the expected value, which would be the sum of X times the relative frequency one. So that was 1.633. How does that compare? 1.67, it's not far off. The variance, well, there's the variance, deviation 1.22. How does that one compare? Well, 1.18. And I guess that's why I chose to do it 1,000 times. Remember we said the more times you do it, then it should get closer and closer to the theoretical probability. In fact, there we go. If I graph the two on the same, you can see how close it matches. The theoretical one there is the orange one, and my simulation was the blue one. So it wasn't far away from it. 17b will play around with binomial distribution.